Hi everyone, welcome to this talk. My name is Etienne. I'm from EPFL, and I will tell you today about how to find better trees to help Santa Claus. And this is a joint work with Lars Rohwedder from Maastricht University. So perhaps I should explain this title first. So let me define to you first the Santa Claus problem. So it's a classic resource allocation problem in which you have n gifts that have to be allocated to m children, and each gift can be given to at most one child, sorry. And each child I gives some value Vij to gift j. And so these Vij, they can be unrelated. So this is a problem coming from scheduling. So sometimes the gifts, they are called jobs and the children are called machines. And what's the goal of Santa Claus is basically we want to find the fairest allocation in the sense that we want to maximize the happiness of the least happy child. We want to maximize the minimum. Okay. So the formal goal, we want to find an integral assignment of the jobs to the machines so that each job is given to at most one machine. And we want to maximize this minimum value among all the machines. And we see that the happiness of each child is just a linear function. It's just the sum of the gifts that you give to him. Okay, so that's the Santa Claus problem. So let me just give you a quick example so that we are all clear on the setting. Imagine I have these 3 children on the left and these 4 gifts on the right, and each child gives me its valuation. So for instance, the first child gives value 10 to the Game Boy, 3 to the hat, 0 to the soccer ball, so I didn't draw the edge, and 8 to the car. And here is a feasible allocation. You can check that no gift is given to more than one child. And like I said, the happiness is a linear function. So the second child is given 2 gifts of 7 plus 3. So his valuation is 10. And now we look at what's the minimum valuation in this allocation, who is the least happy. And these two, they get only 10. So the value of this allocation is 10. And this is this minimum number we're trying to maximize. So why do we care about this problem? First is, well, it's a very basic notion of fairness, one of the simplest to explain from scratch. And also because there's an important open problem about this max-min problem. So about the Santa Claus problem, there's the question is, can you get a constant factor approximation for this problem? And there's a very related problem in which we swap the two. So Santa Claus was maximizing the minimum. If you want to minimize the maximum, it's called max-span scheduling on unrelated machines. And there's also a long-standing open problem to give a better than 2 approximation. And also very interesting, there is a kind of a common belief that these 2 questions are equivalent. So you can get constant factor for Santa Claus if and only if you can get better than 2 for max-span scheduling. I mean, that's a conjecture. But that's also interesting from that point of view because the techniques on the Santa Claus problem, they often seem to often transfer for the max-span scheduling problem. So that's kind of the 2 main motivation of this problem. Now let me explain to you a bit more what we are doing in this paper. In this paper, we consider a special case of the Santa Claus problem that is called max-min arborescences. So in this problem, we're given a directed graph. Let's look at the picture here, a directed graph. And inside that directed graph, there are 3 types of vertices. One vertex is special, it is the source. And other vertices in red, they are sinks. And the remaining vertices, we call them normal vertex. And now I have a number k in mind. And I want to find an arborescence that is rooted at the source and such that every vertex that is in the arborescence and is not a sink has out degree k. We want an arborescence that maximizes the minimum out degree. So maybe it's not clear so far what it is the problem. So let's just see an example. Here's a feasible solution for k equals 3. You can check that the set of blue edges, they form an arborescence rooted at the source and all the edges are oriented away from the source. You can check that the source has out degree 3 and every vertex that is not a sink and is in the arborescence has out degree 3. So that's a feasible solution for k equals 3. And for instance, in that graph, k equals 4 is not possible because then we would need to give this edge to the source. But then this vertex will need out degree 4, but he has only 2 outgoing edges. So k equals 3 is the best possible in that graph. Another question is, I give you any directed graph, can you find the biggest case so that there's such an arborescence? So I'm not proving formally why it's a special case of the Santa Claus problem, but it's fairly intuitive and hinted in the name. We want an arborescence that maximizes the minimum out degree, and Santa Claus was simply maximizing the minimum happiness. So this max-min arborescence problem, it's a special case of the Santa Claus problem. And now the question is, why do we care about that special case? Why is it significant for the general problem? And to understand this, we need to look at the state of the art. So the state of the art, on the positive side, there is only polynomial approximation for both problems. So you can check that, you can see that for the Santa Claus problem, we are actually very, very far from getting constant factor. We only have polynomial approximation. And in the quasi-polynomial time regime, we also have polylogarithmic approximation for both problems. So these two polylog are similar, just the degree of the polynomial here is slightly higher. And so they look very similar, the state of the art for both problems. And they are similar for a good reason, is that the paper that gives, the paper of Chakravarti, Shuzoy, and Khanna that gives the state of the art for the general Santa Claus problem, at the heart of their algorithm, there is some kind of reduction to some slightly more general arborescence problem. But really, yeah, at the most challenging part of the algorithm is to actually find some kind of arborescences that maximizes minimum out degree. So, there's a hope that if you make progress on that special case, max-min arborescence, then you will make progress on the general case. Or at least you will get techniques that will be useful in the general case. And second motivation for the max-min arborescence problem, that is always good to remember, it's a special case of the Santa Claus problem. So, if you want a constant factor for Santa Claus, you need a constant factor for max-min arborescence. Okay, so that's, and on the negative side, the only hardness is factor 2 approximation. So what we show in this paper, basically we get a hardness of approximation for max-min arborescence, and we get the polylog n down to polylog log n in the quasi-polynomial time regime. And this is, I think it's an exciting result because, well, the log n was a good barrier for that problem. So we'll come back to this later, why it was a good barrier. And yeah, in the rest of this talk, I will mostly explain how we get this polylog log n approximation in quasi-polynomial time for max-min arborescence. So first, to understand our result, we need to review a few ideas from previous works. First, well, if you want a polylog log n approximation, you can assume that the optimum is at least polylog log n. Why is that? Is because 1 over opt approximation is trivial. You just find one directed path from source to a sink. It gives out degree 1 to everyone. So it's 1 over opt away from optimum. So if the optimum is less than this, you already have your polylog log n approximation. Then what you can do is you can write an integer linear program formulation of the problem in a very intuitive way. You have a variable xe for each edge in the graph, each edge e in the graph. And well, if x is 1, it means you take the edge. X is 0, you don't take it. And then you have very natural constraints. The in degree of every vertex should be at most 1 because it should be an arborescence. The out degree of the source should be at least k. And if a vertex that is not a thing gets into the arborescence, then its out degree should be at least k times the in degree. So that's a very natural integer formulation of the problem. So there's some trick that is important and appears in previous work is already you can relax that in degree at most 1 constraint to in degree at most c for some c that we call congestion. And well, why you can do that is because if you have a solution that is out degree k and congestion c, then you can transform it easily in polynomial time into a solution that has out degree k by c and in degree 1. So a feasible solution of out degree k by c. So basically, if you have a c here instead of 1, then you can push this congestion c into the approximation ratio. So of course, now the natural thing is you can just relax the integral constraints here to obtain a linear programming relaxation of the problem. But well, here this doesn't work because of the following type of example. There's a big integrality gap. Imagine I have this direct graph, and the source has k-squared outgoing edges, then the naive relaxation will tell you that there is a feasible solution for out degree k. But clearly, you cannot do better than out degree 1 integrally, because if you take any of these vertices, then he has out degree at most 1. So it's a polynomial integrality gap, so there's no way you get polylog log n approximation with this, or even polylog n. And similar examples, slightly more complicated, also show that the configuration linear program also has polynomial integrality gap for the max-min arborescence problem. And the configuration LP was a very popular relaxation. Is a very popular relaxation in the context of the Santa Claus problem. So it's also interesting. It's also good to know that for this max-min arborescence, it doesn't work. Okay, so like the idea to get around that problem that appears in previous work is basically the previous authors, they noticed that somehow you need to remember not only one variable per edge, but you need one variable per path. You need somehow to remember the path that you took to arrive at every vertex. So formally, you can just use standard LP hierarchies to lift and project the linear program from relaxation. And what you get is the following linear program. You have one variable for each path P that starts at the source. And what the constraints that you have is basically you have a kind of demand constraint. If I have a path P that does not end at a sink, then it should be continued one step. Sorry, so I can look at all the paths Q that continue that path P for one more vertex, like one more step away. Then all these paths Q together, they should sum up to at least k times how much you took that path P. Then you have also natural capacity constraints. If I look at any path P that ends at a vertex V, then I should look at all the paths Q that contain P as a prefix and end at V. Then the sum of all these paths Q, they should be at most how much I took the path P. So it's natural capacity constraint. So I'm sure you can convince yourself that integral arborescences, they satisfy all these constraints. So this is indeed a relaxation of the problem. But of course, now it's not clear what to do with this relaxation, because like a graph has exponentially many paths. So notice that here it would mean that I have exponentially many variables and exponentially many constraints. And a crucial trick that appears in previous work is that if you're fine with losing a factor 2, then you can assume that your integral solution has depth at most log n. So basically, you can just write this relaxation only for paths of length at most log n. So now suddenly your relaxation has only quasi-polynomially many constraints and quasi-polynomially many variables. And that's the relaxation that the previous works used. And now the algorithm in previous works is now can be described as the following 3 steps. First, we solve that relaxation I was talking about. So this takes quasi-polynomial time. Then you do an intuitive randomized rounding. And at the end, you prove that using Chernoff bounds that the maximum in degree, so the maximum congestion on every vertex is at most C, for C to be polylogarithmic. So the randomized rounding is fairly intuitive. It's basically, we start at the source here, and we look at all the paths of length 1 that start at the source, and I pick k of them at random. Then let's say I pick these 2, brown one. Then for each of these that I took, I look at all the paths that contain this brown path as a prefix and continue one step further. And again, I repeat and I take k of them at random. And these paths that I select will be like the children of that path of length 1. And I repeat this, I propagate this process until I reach the sinks where I can stop the arborescence. And here what we mean by picking randomly is the very intuitive way. Is like if you have several paths to choose from, you just pick them with probability proportional to the LP value. And of course, there's some necessary pruning. Basically, if I took these 2 paths for at distance 2, then all the other paths that were possible and were not selected, then we can just delete them. So that's the previous algorithm. And now they can show using Chernoff bounds that if you do this, you have congestion that is polylogarithmic everywhere. So that gives you your polylogarithmic approximation ratio. So of course, now the first question is this rounding better than log n? And our first contribution is to show that no, it's not better than log n, in the sense that if you do that intuitive rounding, what can happen is that for a distance of log n, so log n steps of that rounding, everything goes fine. You get a perfect tree of in degree 1. So everything seems perfect so far, but all the things they are at distance log n. And when you arrive at the thing, they all get congestion log n simultaneously in expectation. So that example is quite problematic because it just says that, well, all the vertices that I selected just one step before the sinks, they all want the same sinks, and there's no way around this. So if you do that randomized rounding, you will be stuck with a log n approximation ratio. That's why we thought also log n was a good barrier. And what this teaches us is that basically you need to be able to get below log n approximation. You need to be able to remove some parts of the tree. So to be a bit more concrete, here's an easy fix to that instance, is that instead of picking k children of each path, according to like where k is what the LP value, the LP tells you is feasible, instead of picking k, you pick only k by 2 children for each path that you selected. And what's the effect of that is that basically every time you progress one layer, then the expected congestion on the sinks decreases by a factor half. So, if we are far away, then we should get rid of this log n congestion. So that's an easy algorithm that fixes the previous example, but we don't know how to analyze this better in the general case. But it still teaches us something useful. It gave us a simple trick that we call top-to-bottom pruning. Is the following trick. Imagine you're giving me an integral solution. Then I can remove some parts of the solution by just starting at the source. I look at the children of the source, and the source just keeps half of them at random, uniformly at random. Then I look at the surviving children of the source, and I look for each of these surviving children. I look at its own children, and he repeats the same. He keeps half of them at uniformly at random. And I repeat this until I reach the sinks. So what's the strength of this is there's a hope. So first, notice that the odd degree is not decreased too much by this trick. Just every vertex loses half of its children, so you only lose a constant factor. And there are a few things that are useful. First, if you have a path of a length d, then if you apply this top-to-bottom pruning, then the path survives with probability 1/2 to the d. So the intuition is that if you have congestion that is far away from the source, then this congestion should decrease a lot. I know there's a more concrete hope. Let's say you give me a solution with congestion log n. Can we fix it with this trick? Just using one round, just using this top-to-bottom pruning once, can we fix it? So the answer, there's still a significant issue with this, is that imagine in my integral solution, I have the following structure. So this vertex has congestion log n, but these log n paths, they all share for a very long time the same path, and then they just split 2 steps away from the vertex. Now it's clear that if you apply the top-to-bottom pruning, you cannot fix this instance because, well, after the pruning, the congestion at the vertex will be always either 0 if one of the edges in the long path is cut, or if all the edges in the long paths survive, then the congestion at vertex will be proportional to log n with high probability. So basically, it's not helping you, the top-to-bottom pruning. You still have one vertex with logarithmic congestion. So what we did to get rid of that type of bad structure that gives us high correlations, we have a new definition, a new concept that we call locally good solutions. So locally good solution is a solution with congestion polylogarithmic. But then if I look locally, so inside any subtree of height log n, then the congestion should be only at most polylog log n. So for instance, that structure, it's not locally good because if I look at the subtree rooted at that vertex, then you see that at that distance 2, I already have congestion log n. So that new definition was kind of crucial to get rid of bad correlations. And now we can state our algorithm. Basically, we solve the same relaxation in quasi-polynomial time as previous works. And then from the fractional LP solution, we obtain a locally good solution. And then we transform a locally good solution into a solution of congestion polylog log n. And that's how we get our approximation ratio. And both steps use heavily Lovász local lemma. So now to finish this talk, I just like to give you a taste of how we do the second step. So just an illustration of our techniques on a simplified example. So let's assume the following. So remember, I want to transform a locally good solution into a solution of congestion polylog log n. So let's just have slightly stronger assumptions. Let me assume that we have a solution of congestion log n, but locally there is no congestion. So inside each subtree of height log n, there's congestion at most 1. And let me also assume that the R degree is polylogarithmic. Then I want to apply Lovász local lemma, so my random experiment will be the top to bottom pruning. And my bad even BV will be basically that if I look at any vertex V, then more than polylog log n of the paths ending at V survive. And I just limit myself to the last log n steps. Okay? So I claim the following. First, the probability of any bad event is at most exponentially small in log n. Why is that? Let's just look at the picture. So remember that locally there's no congestion. So these red paths, they have to be disjoint, which means that with the pruning, they survive independently of each other. And now note that each path survives for probability 1/2 to the log n. So it's 1 by log n. And they can be at most log n of them because the global congestion is log n. So the congestion on vertex V is basically a sum of 0, 1 random variables that are independent, and the total expectation is at most 1. So you can apply Chernoff bound, and you get this probability. Second claim is that any bad event depends on at most this many other bad events. So that's where we use that K is polylogarithmic here. And here the proof is also very simple. Think about it. It's, well, a bad event V depends only on the random choices made by vertices that are close ancestor of V. So they are a distance at most log n, and so they are at most log n times log n of these. And now the random choice made by a vertex, it can only influence all the bad events for some other vertex if that other vertex is in the closed subtree rooted at vertex U. So there are at most this many. So you do the product of the two, you get at most this many other dependencies. And you can show that the dependencies is at most exponential in polylog log n. Okay, so now if you know Lovász local lemma, the product of dependency times probability is small, so you can apply Lovász local lemma, and we can use the pruning in a way that guarantees that no bad event happens, which means we get a solution of global congestion at most polylog log n, and that's how we get our polylog log n approximation ratio. So I think this is a good illustration of the type of technique that we use in this paper. So now I just, of course, there's a few things I didn't talk about. What if K is bigger? That's more challenging. We need different pruning tricks. And also, how do we get a locally good solution? Also, it's not trivial, but you can still use Lovász local lemma in similar ways. So to finish, well, in summary, the main result is we give a polylog log n approximation for max mean arborescences in quasi-polynomial time. What is interesting is that it's the first sublogarithmic approximation without using the configuration LP. And we should mention that we can extend our results to multiple source using local search. So multiple source, I mean, we want one arborescence for each. You have several sources in your graph, and you want one arborescence for each, and the arborescences shouldn't overlap. And I'd like to finish by a few open questions. So of course, the most obvious one is, can we generalize this technique to the general Santa Claus problem? That would be very interesting to see. And also, yeah, what about polynomial time? Because here we only talk about quasi-polynomial, but it would be very interesting to improve on the polynomial approximation factor that is in polynomial time, which is the best that we know so far. So that's the end of my talk. I'd like to thank you all for your attention.